This program is brought to you by Stanford University. Please visit us at stanford.edu.
This quarter, we're going to learn about field theory, classical field theory. Fields such as the electromagnetic field, gravitational field, other fields in nature, which I won't name right now, propagate, which means they change according to rules which give them a wave-like character moving through space. And one of the fundamental principles of field theory, in fact, more broadly, nature in general, is the principle of relativity. The principle of special relativity in this particular case. The principle of special relativity, well, let's just call it the principle of relativity, goes way back. It was not an invention of Einstein's. I'm not absolutely sure when it was first announced or articulated in the form which I'll spell it out. I don't know whether it was Galileo or Newton or those who came after them, but those early pioneers certainly had the right idea. It begins with the idea of an inertial reference frame. Now, an inertial reference frame, there's something a bit tautological about an inertial reference frame. Newton's equations, F equals ma, are satisfied in an inertial reference frame. What is an inertial reference frame? It's a frame of reference in which Newton's equations are satisfied. I'm not going to explain any further what an inertial reference frame is, except to say that the idea of an inertial reference frame is by no means unique. A reference frame, first of all, what does a reference frame entail? A reference frame, first of all, entails a set of coordinate axes in ordinary space, x, y, and z, and you know how to think about those. But it also entails the idea that the coordinate system may be moving or not moving, relative to whom? Relative to whomever. We sitting here, or you sitting here in this classroom here, define a frame of reference. We can pick the vertical direction to be the z-axis, the horizontal direction along my arms here to be the x-axis, x plus that way, x is minus in that direction. And which one have I left out? I've left out the y-axis, which points toward you from me. So there are some coordinate axes for space, x, y, and z. And in addition, to specify a frame of reference, one also imagines that this entire coordinate system is moving in some way relative to you sitting there, presumably with a uniform velocity in a definite direction. If your frame of reference is an inertial frame of reference, in other words, if when you throw balls around or juggle or do whatever you're supposed to do in an inertial frame of reference, if you find yourself in an inertial frame of reference, then every other frame of reference that's moving with uniform velocity relative to you, now remember what uniform velocity means. It doesn't just mean with uniform speed, it means with uniform speed in an unchanging direction. Such a frame of reference is also inertial. If it's accelerated, if it starts standing still and then suddenly picks up some speed, then it's not an inertial frame of reference. All inertial frames of reference, according to Newton and also, I think, also Galileo. Galileo was often credited with the idea, but I never read enough of Galileo to know whether he actually had it or not. Neither did I read enough of Newton. They both wrote in languages that I don't understand. What was I saying? Oh, yes. Right. According to both Newton and anybody else who thought about it very hard, The laws of physics are the same in all inertial reference frames. Laws of physics meaning F equals ma, the forces between objects, all the things that we would normally call laws of nature or laws of physics don't distinguish between one frame of reference and another. If you want a kind of pictorial example that I like to use a lot when I'm explaining this to children or to grown-ups, I like to think about the laws of juggling. There are very definite procedures that you train your body to do in order to be able to juggle balls correctly. Now, you can imagine yourself being in a railroad car, moving with perfectly uniform velocity down the x-axis and trying to juggle. Do you have to compensate for the fact that the train is moving? In particular, when you throw a ball up into the air, do you have to reach over to the right to compensate for the fact that the train is moving to the left, my left, your right? The answer is no, you don't. The laws of juggling are the same in every reference frame, in every inertial reference frame. Whatever you do in one reference frame, you do exactly the same thing, and you'll succeed or fail depending on whether you're a good juggler or not, but it will not depend on whether you're moving with uniform velocity. So the laws of juggling are the same in every inertial reference frame. The laws of mechanics are the same in every inertial reference frame. The laws, Newtonian laws of gravity are the same in every inertial frame, according to Newton. What about the laws of electrical phenomena? Well, there was a clash. The clash had to do with Maxwell's equations. Maxwell's equations were the field equations, the field theory that governed the electromagnetic field and the way that it propagated and sent waves, electromagnetic waves, that we ordinarily call light or radio waves or so forth. And the fundamental dilemma, as you all know, I'm sure you all know, the fundamental dilemma was both according to, well, here was the dilemma. Maxwell's equations said light moves with a certain velocity. If you take the various constants that appear in Maxwell's equations and put them together in the right way, you get the velocity of waves moving down an axis. And that velocity comes out to be a certain number out of Maxwell's equations. You have two choices. One is to believe that Maxwell's equations are true laws of nature, as good as any other laws of nature, in which case the principle of relativity says they should be the same in every reference frame. But if it follows from Maxwell's equations that the speed of light is 3 times 10 to the 8th meters per second, which is about what it is, if it follows from Maxwell's equations that light moves that fast, and if Maxwell's equations are laws of physics, fundamental laws of physics, and if the laws of physics are the same in every reference frame, then the speed of light must be the same in every reference frame. But that was very hard to swallow, because if a light beam is going down that axis, and you chase it and run along with it at, let's say, 3/4 of the speed of light, then you ought to see that light ray moving much more slowly than 3 times 10 to the 8th meters per second relative to you. On the other hand, the light ray going in the other direction, since you're sort of running into it, you should see going even faster. So all these possibilities could not simultaneously be correct. That the laws of nature are the same in every reference frame, and that Maxwell's equations are laws of physics in the same sense that Newton's laws of physics, namely the same in every reference frame. Something had to give. Well, the point was, of course, that they were good laws of nature and that they were the same in every reference frame. The thing that had to give is our concepts of velocity, space, and time, and how we measure velocity, especially velocities which are up near the speed of light. Now, I'm not going to spend the full amount of time that I did previously on the special theory of relativity. That can be found on lectures from how long ago? They're on the internet, I believe. Relativity and electromagnetism. I think that was maybe about 3 quarters ago. I've lost track. Yeah, they're up there. They're on the net. And they're the lectures on relativity, special relativity, and electromagnetic theory. We're just going to cut through it real fast. We're going to cut through the basic ideas of relativity a little more mathematically than I would do if I were teaching it for the first time. If I teach it the first time, I tend to teach it the way Einstein first conceived of it. How do you measure distances? How do you measure velocities? How does the propagation of light influence these things? Instead, I'm going to take a more mathematical view of it and think about the properties of various kinds of coordinate transformations. Coordinates now consist not only of x, y, and z, but also time, t. So imagine every event in the world is characterized by, just like every particle would be characterized by a position, x, y, and z, every event taking place in space-time is characterized by 4 coordinates, x, y, z, and t. Let's suppress for the moment y and z. Let's just forget them for the moment and concentrate on x and t. That would be appropriate if we were mainly interested in motion along one axis. Let's focus on that. Motion along the x-axis. Let's suppose there is no motion along y and z. Then we can forget y and z for the moment, momentarily. We'll come back to them. And think of motion along x and t and the various reference frames that might be moving along the x-axis. All right, here's time vertically. Here's space horizontally. Physicists always draw space horizontally and time vertically. I found out that mathematicians, or at least certain computer scientists, always draw time going horizontally. I didn't know that. And I got into an enormous argument with a quantum computer scientist, which was ultimately resolved by the fact that he had time going horizontally and I had it going vertically. These are traditions, I guess. Traditions grow up around subjects, but time is north and x is east, I guess. Or at least time is upward. Yeah?
The mathematicians are thinking of the independent.
Yeah, that's the point. That is the point, yes. They're thinking of time as the independent variable, and everybody knows that it's a law of nature that the independent variable should be horizontal. Right. All right. Now, let's imagine a moving observer moving down the x-axis with a velocity v. Let's take his origin of spatial coordinates. His origin of spatial coordinates at time t equals 0 is just at the same. Let's assume that I'll be the moving observer. I move down the x-axis. I am my own origin. There's nobody who is your origin. That seat is vacant over there, so that absence of human over there is the center of the x coordinates in your frame. I'm the x prime coordinates, and of course, I, being very egocentric, will take my x origin to be where I am. There I do. I move down the x-axis. We pass each other. Our origins pass each other at t equals 0. So that means at t equals 0, your axis and my axes are the same, or your origin and my origin is the same. But then as I move down the x-axis, my coordinate center moves to the right. It moves to the right. That's supposed to be a straight line. It's as good as I can do under the circumstances. That's a straight line, and it's moving with velocity v, which means it's x prime equals, it means x equals vt. But it's also, that's the way you describe it in terms of your coordinates. My center, you describe by saying x equals vt. How do I describe it? I just say x prime, my coordinate, x prime is 0. X prime equals 0 is the same as x equals vt. All right, what's the relationship between x prime and x and t? Well, it's easy to work out, if you believe this picture. The x prime coordinate is the distance from my origin. The x coordinate is the distance from your origin. So one of these is x, the other is x prime. The upper one here is x prime, the lower one here is x. And the relationship between them is that they differ by an amount vt. In particular, x is equal to x prime minus vt, or x prime is equal to x plus vt. Do I have it wrong? Yes, I do. X prime is x minus vt, and x is x prime plus vt. Yeah, I think I have it. That's correct now. All right, what about time itself? Well, according to Newton, and according to Galileo, and according to everybody who came afterward up until Einstein, time is just time is just time is just time. There was no notion that time might be different in different reference frames. Newton had the idea of a universal time, sort of God's time. God up on his cloud, ticking off with his super accurate watch. And that time was universal for everybody, no matter how they were moving. And so everybody would agree on the time of any given event in this map of space and time here. And so the other equation that went with this is that t prime is equal to t. Let's forget the top equation here. Let's just forget it. One might say that this was the Newtonian or the Galilean transformation properties between x and t, your coordinates, and the coordinates that I ascribe to a point in space-time. Now, let's examine a light ray moving down the plus x axis. If it starts at the origin here, then it moves along a trajectory which is x equals ct, c being the speed of light. Now, shortly I'm going to set c equal to 1. We're going to work in units in which c is equal to 1, but not quite yet. Incidentally, once you understand a bit of relativity, working in coordinates in which c is not equal to 1 is about as stupid as using different units for x and y. If we used yards for x and feet for y, then we would have all kinds of funny factors in our equations, which would be conversion factors from x, which is measured in feet, to y, which is measured in yards.
Log scale has its uses. Log scale has its uses.
Well, I don't know. Log scale? I don't think we're going to do log scale. Well,
like compound interest.
Yeah. I'm not sure what's getting it, but okay.
I'm just saying it is quite often in practical circumstances that one uses different scales.
Yeah, sometimes there might be a good reason. I mean, it wouldn't be totally unreasonable for a sailor to use different units for horizontal direction and vertical direction. I mean, he's used to moving around horizontally. He might use, miles versus fathoms or something. Nautical miles versus fathoms, yeah.
I'm not sure if this question is relevant, if you'll pardon me.
Sure it's relevant.
But when you talk about a frame of reference, do you need to specify a period of time? Because obviously go back 15 billion years, there is no...
Yeah. We're ignoring now the fact that the universe began at some time, and we're imagining now, as Newton did, and as the early Einstein did, that the universe has just been here forever and ever and ever, unchanging, totally static, and space and time have properties which don't change with time. Now, of course, that's incorrect in the real world, and at some point we will take up the subject of cosmology and find that's not right. But as long as we're interested in time intervals, which are not, I suspect this is what you're getting at, as long as we're interested in time intervals which are not too long, in particular time intervals over which the universe doesn't expand very much and so forth, we can mainly say the properties of space don't change over a period of time, And so everything just stays the same as it always was. Is that what you're asking?
Well, it seems that this assumption, if it is made, it leads to what you're describing. So, so the question is, would that eventually lead to some?
The point is, it doesn't lead. It doesn't lead to what I'm describing. Okay. Where there's this room for different formulas here. This is a formula which was based on an assumption, the assumption being that time is universal. That's what Einstein found was wrong. Basically what he found is that when you're in a moving frame of reference, two different observers will not agree about what time a particular event takes place. This is the culprit here, this one, and some modifications to this one. But in any case, to see what's wrong, let's go to Maxwell's equations. Maxwell's equations say that light always moves with this velocity, c being some numbers in meters per second. Okay? 3 times 10 to the 8th meters per second. We will later, as I said, say c equals 1. Let's imagine a light beam moving down the x-axis. Let's describe how x prime sees it. In other words, you see the light move this way to the right. How do I see the light? Well, let's see what I see. Let's just work it out. X prime will be x, which is ct for that light ray, minus vt, which is the same as c minus vt. All this says is that I see the light moving with a diminished velocity, a velocity c minus v. Why is that? Because I'm moving along with the light, so naturally I see it move slowly. But slow compared to what you see it. Okay. What about the light going in the other direction? Supposing it was a light beam going in the other direction, then how would you describe it? You would describe it as x equals minus ct. And if I do exactly the same thing, I will find that x prime is equal to x, that's minus ct, minus vt, which is the same as minus c plus v times t. So what this says is that I will see the light moving also in the negative direction, that's the minus sign, but I'll see it moving with an enhanced velocity, c plus v. If this were the right story, and if these were the right transformation laws for space and time, then it could not be the case that Maxwell's equations are laws of physics or laws of nature in the sense that they were true in every reference frame. They would have to be corrected in moving frames, just like the juggler who had to reach to the right, who didn't actually, but who thought he had to reach to the right to collect the ball when the train is moving. The physicist interested in light beams would have to correct things for the motion of his reference frame. Now, it's an experimental fact that this is not the case, that you don't have to correct for motion. It was the famous Michelson-Morley experiment. Einstein, he just rejected, he just felt this can't be right. Maxwell's equations were much too beautiful to be relegated to the approximate or to the contingent on which reference frame. And so he set about to find a framework in which the speed of light would be the same in every reference frame. And he basically focused on these equations, and after various very, very beautiful Gedanken experiments, thought experiments about light and about measuring and so forth, he came to a set of formulas called the Lorentz transformations. I'm going to explain them, the Lorentz transformations, in a more mathematical way. Not fancy mathematics, but just we want to get right to the heart of it and not spend 3 weeks doing it. The best way is to set up a mathematical problem. But before I do, let me set up a different mathematical problem, which is, for most of you, you've seen me do this before, but nonetheless, let's go through it again. The problem of rotation of coordinates. We're going to do this quickly. Let's just take spatial coordinates now for the moment. Two-dimensional spatial coordinates. Let's forget x and t and just concentrate on x and y. Two coordinates in space. Instead of events in space-time, concentrate on a point in space. A point in space has coordinates, and we can determine those coordinates, the x and y coordinates, just by dropping perpendiculars to the x-axis and the y-axis. And we would describe this point as the point at position, let's just call it xy. Now, there's nothing sacred about horizontal and vertical. So somebody else might come along, some crazy mathematician, a really nutty one, who wants to use coordinates which are at an angle relative to the vertical. Maybe a couple of beers and you don't know the difference between vertical and what we should give this direction a name. Oblique. Yeah. All right. The oblique observer, the blue observer, can blue be seen? Yep. Everybody can see blue. Okay. Good. The blue observer also characterizes points by coordinates, which he calls x prime and y prime. The x prime and the y prime coordinates are found by dropping perpendiculars to the x prime and the y prime axis. So here's x prime, here's y prime, and given a point xy, there's a rule, there must be a rule. If you know the value of x and y, you should be able to deduce the value of x prime and y prime if you know the angle between the two coordinates, between the x coordinate and the x prime coordinate. And the formula is simple. We've used it in these classes many times. I'll just remind you what it is. It's x prime is equal to x times cosine of the angle between the two frames, between the two coordinate systems, minus y times sine of the angle. And y prime is equal to minus, plus, I think, x sine of theta plus y cosine theta. I just want to remind you about a little bit of trigonometry. All of trigonometry is encoded in two very simple formulas. I've used them.
The signs on these signs are wrong.
You're right. Let's see. Hold on.
X prime is bigger than x for small theta.
You say the signs here are wrong.
Yeah. So it's
x
plus
prime
is bigger than x.
Is it?
Yeah.
Let's see.
If you rotate it to the next, so that y prime is 0, it's further out.
X prime. Do I have it backward?
Yeah.
I don't know.
I'm not sure.
I'm not convinced.
No, not either. So let's see.
Just make sure the length
X
is
prime is the little perpendicular there on.
No, y prime is a
No,
little.
that's y prime.
Yeah.
So y prime is.
This is y prime here.
Right.
Right. That's y prime
And
here.
x prime is bigger than x, so there has to be a plus sign on the second
How
term.
do you know x prime is bigger than x? Let's see. Yeah, x prime is bigger than x. Yeah, x prime is bigger than x. Looks like that's probably right. Probably sine. But then this one must be negative. Yeah. Okay. There's an easy way to correct for it, another way to correct for it. Just call this angle minus theta. That would also do the trick, because cosine of minus theta is the same as cosine of theta, and sine changes sign when you change theta to minus theta. So if instead of calling this angle theta, I called it minus theta, then my previous formulas would be right. It's true, but it's an excuse. All right, what do we know about sine and cosine? It's important to understand sine and cosine. Everything you ever learned about trigonometry can be codified in two very simple formulas if you know about complex numbers. The two very simple formulas are that cosine of theta is e to the I theta plus e to the minus I theta over 2, and sine of theta is e to the I theta minus e to the minus I theta over 2I. Those two formulas contain everything about trigonometry. You don't have to know any other formulas other than these. For example, I will assign you the homework problem of using these two formulas to find cosine of the sum of two angles. But the way you would do it is just write the sum of two angles in here and then re-express the exponentials in terms of cosine and sine. That's easy to do. E to the I theta is equal to cosine of theta plus I sine theta, and e to the minus I theta is cosine of theta minus I sine theta. So work through these formulas, get familiar with them. They're extremely useful formulas. Once you know them, you will never have to remember any trigonometric formulas again. All right? The other thing to know is that e to the I theta times e to the minus I theta is 1. All right? E to the anything times e to the minus the same thing is 1. Those things characterize all trigonometric formulas. In particular, as was explained to me by Michael a number of times, if we multiply e to the I theta times e to the minus I theta, we will get 1 on this side. But on this side, we will get cosine squared of theta plus sine squared of theta. Not minus sine squared, but plus sine squared. Cosine squared, and then minus I squared sine squared. That gives us cosine squared plus sine squared. Cosine squared theta plus sine squared theta. So that's equivalent to the fact that e to the I theta times e to the minus I theta is 1. All right. Now, the most important fact that, again, follows from the simple trigonometry is that when you make the change of coordinates from xy to x prime y prime, something is left unchanged. Namely, the distance from the origin to the point xy. That's something which is, you count the number of the molecules along the blackboard from here to here, and that doesn't change when I change coordinates. So the distance from the origin to the point xy has to be the same independent of which coordinate axes we use. Well, let's take the square of that distance. The square of that distance, we know what it is. It's x, let's call it s squared. I'm not sure why I use s, but s for distance. S for distance. S for space. I think it must be for space that I'm using it. For the spatial distance from the origin to the point xy. We know what that is. It's Pythagoras' theorem, x squared plus y squared. But as I said, there's nothing special about the xy axes. We also ought to be able to calculate it as x prime squared plus y prime squared. Well, it's not too hard to work out that x prime squared plus y prime squared is x squared plus y squared. It's easy to do. X prime squared plus y prime squared will have x squared cosine squared theta. It will also have x squared sine squared theta. When you add them, you'll get x squared plus y squared. You know the rigmarole. So it follows from cosine squared plus sine squared equals 1 that x prime squared plus y prime squared is equal to x squared plus y squared. Work that out. Make sure that you have this under control, that you understand why, from the trigonometry, not from the basic physics of it or the basic geometry of it is clear. Make sure that you understand that you can see that from the trigonometry. Okay. One last thing about sines and cosines. If I plot on the blackboard for every angle, if I plot sine or cosine along the horizontal axis, supposing I plot cosine of theta along the horizontal axis and sine of theta along the vertical axis, then if I plot all possible angles, they will correspond to a bunch of points that lie on a unit circle. Why on a unit circle? Because sine squared plus cosine squared equals 1. So one might call the properties of sine and cosine the properties of circular functions. Circular in that they're convenient for rotating, they're convenient for describing unit circles. Points on unit circles are described in terms of coordinates, which are cosines and sines of angles and so forth. It's natural to call them circular functions. These are not the functions that come in to the transformation, the new transformation properties. First of all, these are wrong. I don't want to use x. Let's x. Yeah. No, just wrong. Newton had it wrong. Newton or Galileo or whoever it was who postulated it. Einstein modified it. Now, we're going to have to make sure that Einstein's modification doesn't change things in situations where Newton's equations were good approximations. The situations where Einstein's modifications are important is when we're talking about frames of reference moving very rapidly, up near the speed of light. Before the 20th century, nobody or nothing had ever moved faster than 100 miles an hour, probably. Well, of course, some things did. Light did. But for all practical purposes, light didn't travel at all. It just, when you turned on the switch, the light just went on. So light didn't travel. Nothing in anybody's experience, direct experience, traveled faster than 100 or 200 miles an hour. And, well, I should say, nothing traveled faster than 100 miles an hour and lived to tell about it. So all of experience was about very slow velocities on the scale of the speed of light. On the scale of such velocities, Newton's formulas must be correct. They work. They're very useful. They work. Newton got away with it, so they must be good approximations. It had better be that whatever Einstein did to the equations, in particular to these two equations here, had better reduce to Newton's equations in the appropriate limit. Okay, let's come back now to light. Light, according to the Newton formulas, doesn't always move with the speed of light. But let's try to figure out what it would mean of a better formula, of a replacement for this, that light always moves with the speed of light. First of all, let's set the speed of light equal to 1. That's a choice of units. In particular, it's a choice of the relation between space units and time units. If we work in light years for distance and years for time, then light moves 1 light year per year. The speed of light is 1. If we use seconds and light seconds, it's also 1. Whatever scale we use for space, if we use for time, the time that it takes light to go that distance, 1 unit of space, if we use that for time units, then the speed of light is equal to 1. Now, from the ordinary point of view of very slowly moving things, those are odd units. But if we were electrons with neutrinos and whizzing around like photons, they would be the natural units for us. Speed of light equals 1. So let's set the speed of light equal to 1. As I said, it's just a choice of units. And then a light ray moving to the right just moves along a trajectory x equals t. C is just equal to 1. A light ray moving to the left is x equals minus t. How can we take both of these equations and put them together? Sorry, x equals minus t. Can I write a single equation which, if it's satisfied, is a light ray either moving to the left or to the right? Yes. Here's an equation. x squared equals t squared, it has two solutions, x equals t and x equals minus t. The two square roots, well, x squared equals t squared is equivalent to either x equals t or x equals minus t. In other words, this equation here is a necessary and sufficient condition for describing the motion of a light ray either to the right or to the left. Supposing we found a replacement for this equation which had the following interesting property, that whenever, let's write it this way, x squared minus t squared equals 0. This is even better for our purposes. X squared minus t squared equals 0. That's the necessary and sufficient condition to describe the motion of a light ray. Supposing we found a new set of rules, a new set of transformation properties which had the property that if x squared minus t squared is equal to 0, then we would find that x prime squared minus t prime squared is equal to 0. In other words, supposing this implied this, and vice versa, then it would follow that what the unprimed observer, you in your seats, see as a light ray, the primed observer, me moving along, also see as a light ray, both of us agreeing that light rays move with unit velocity. Now, this doesn't work for Newton's formula here. It just doesn't work. If x is equal to t, it does not follow that x prime is equal to t prime. In fact, it says something quite different. Okay? So, the form of these equations must be wrong. Let's look for some better equations. Now, at this point, let's even be a little bit more ambitious. It turns out being a little bit more ambitious actually simplifies things. Let's not only say that when x squared minus t squared is equal to 0, then x prime squared minus t prime squared is equal to 0. Let's say something even bolder. Let's say the relation between xt and x prime t prime is such that x squared minus t squared is equal to x prime squared minus t prime squared. In other words, pick any x and any t and calculate x squared minus t squared. Then take the same point except reckoned in the primed coordinates. In other words, we take a certain event, a light bulb goes off someplace. You say that corresponds to x and t. I say it corresponds to x prime and t prime. But let's require, just to try it out, see if we can do it, let's look for transformations so that x squared minus t squared will always be equal to x prime squared minus t prime squared. That would be enough to ensure that everybody will agree about the speed of light. Why? If x squared minus t squared equals x prime minus t prime squared for all x and t and so forth, then when x squared minus t squared equals 0, x prime minus t prime squared will be 0. And then, if this is a light ray, so is this a light ray. Everybody get the logic? Okay, good. So let's assume now that, let's ask, can we find transformations which have this particular property? Now, it's not so different from looking for transformations which preserve x squared plus y squared equals x prime squared plus y prime squared. It's just a little minus sign. Other than a minus sign here, x squared minus t squared, the look of these two is very similar. And the mathematics is quite similar. Here are the transformations which preserve x squared plus y squared. What are the transformations which preserve x squared minus t squared? Well, they are the Lorentz transformations. They are the fundamental transformations of the special theory of relativity. They're not this, but they're closely related, or perhaps one should say closely analogous to these equations here. But we have to substitute for circular trigonometry hyperbolic trigonometry. So let's go back and remember a little bit about hyperbolic functions instead of circular functions. Well, I didn't want to erase that. All right, these are the basic rules governing circular functions. Cosine theta is equal to this. Sine theta is equal to this. And the e to the I theta in terms of cosine and sine. All right, let's see if we have a, yeah, we do have a blank blackboard here. Let me write, whoops, what did I do here? I erased something I didn't mean to erase. Here it is. Okay. Incidentally, does everybody see how I got this side from this side? You just add and subtract the equations appropriately, and you isolate e to the I theta and e to the minus I theta. That's elementary exercise. All right, hyperbolic functions. What are hyperbolic functions? All right, those are functions of the form hyperbolic cosine cosh. Hyperbolic cosine, first of all, the angle theta is replaced by a variable called omega, which I will call omega. Omega is called a hyperbolic angle. It doesn't go from 0 to 2 pi and then wind around on a circle. It goes from minus infinity to infinity. It goes from minus infinity to infinity. So it's a variable that just extends over the entire real axis. But it's defined in a manner fairly similar to cosine and sine. Cosh omega is by definition, you're not allowed to ask why, this is definition, e to the omega plus e to the minus omega over 2. All we do is substitute for theta, or for omega, theta, I theta, substitute omega. And that gives you hyperbolic functions. Likewise, or similarly, there's the hyperbolic sine. And that's given by e to the omega minus e to the minus omega over 2. Essentially, you throw away all i's out of that formula, out of the top formulas. Just throw away all i's. The equations on the right-hand side become e to the omega equals hyperbolic cosh omega plus sinh omega, and e to the minus omega equals cosh omega minus sinh omega. I think that's right. Is it right? Cosh minus sinh. It is? Yeah, it is right. Okay, now what about the analog of cosine squared plus sine squared equals 1? That simply came by multiplying this one by this one. So let's do the same operation. Multiplying e to the omega by e to the minus omega gives 1. And now that gives cosh squared minus sinh squared. You see, we're getting a minus. What we want that minus. The minus is important. We want to, well, somewhere under here was a formula with a minus sign. Yeah, we want to get that minus into play here. That's cosh omega squared. No, not cos, but cosh squared omega minus sinh squared omega. So it's very similar. Everything you want to know about hyperbolic trigonometry, and the theory of these functions is called hyperbolic trigonometry. Everything you ever want to know is codified in these simple formulas, these and these. And they're more or less definitions, but they're rather useful definitions. Now, yeah, go ahead.
Is it worth mentioning that x squared plus y squared equals constant is a circle,
Yeah.
and x squared minus y squared equals constant?
Not only is it worth mentioning, I was just about to mention it. Sorry, x squared minus y squared is what?
X squared minus y squared equals constant is hyperbola.
A hyperbola, yeah. Right, exactly. So if I were to play the same game that I did here, namely plot on the horizontal and vertical axis the values not of cosine of theta and sine of theta, but cosine, cosh of omega and sinh omega. Let's, in other words, on the x-axis now, we're going to plot cos omega, and on the y-axis, sinh omega. Then this is a hyperbola, not a circle, but a hyperbola. And it's a hyperbola with asymptotes that are at 45 degrees. You can see, let me show you why the asymptotes are at 45 degrees. When omega is very large, then e to the minus omega is very small, right? When omega is very large, e to the minus omega is very small. And that means both cosh and sinh are both essentially equal to e to the plus omega. In other words, when omega gets very big, cosh and sinh become equal to each other. And that's this line here. Cosh equals sinh along this line here. So when omega gets very large, the curve asymptotes to a curve which is at 45 degrees. It's not hard to see that in the other direction, when omega is very negative, that it asymptotes to the other asymptotic line here. So that's why it's called hyperbolic geometry. The hyperbolic angles, the coshes, the sinh play the same role relative to hyperbolas as sines and cosines do to circles. Any questions?
So, let's see.
No questions.
So when cosh omega equals 0, how would you plot that hyperbola?
Well, cosh omega, cosh squared minus sinh squared equals 0? No. No, cosh squared minus sinh squared equals 1 in the same sense that sine squared plus cosine squared equals. It never equals 0. I think you wanted to ask a different question. I think.
When sinh omega equals 0.
Oh. Well, sinh omega equals 0 is the horizontal axis. Cosh omega equals 0 is the vertical axis.
Right, okay.
Well, then it's the x-intercept.
Yeah.
It's the vertex.
Yeah, I was just thinking, here's one point
Yeah.
on the graph. Yeah. All right.
The x-intercept there is 1. Yeah. Because cosh of 0 is 1. To see that, just plug 0 in here. 1 plus 1 divided by 2 is 1. At least it was yesterday. Yeah, it still is. Okay. So now we're sort of starting to cook a little bit. We're starting to see something that has that nice minus sign in it. But what's it got to do with x and t and x prime and t prime? We're now set up to make, let's call it a guess. But it's a guess which is based on the extreme similarity between hyperbolas and circles, coshes and cosines, and so forth. Here's the guess I'm going to make, and then we'll check it. We'll see if it does the thing we want it to do. My formula, instead of being this, we're now going to have, instead of x and y, we're going to have x and t. Time and x Later on, we'll put back y and z. We're going to have to put back y and z, but they're very easy. Okay, so let's start with x prime. X prime is the coordinate given to a point of space-time by the moving observer, namely me. And I'm going to guess that it's some combination of x and t. Not too different, but not the same as, where is it? X prime equals x minus vt. I'm going to try cosh omega x. That's right, x cosh omega minus t sinh omega. Sort of in parallel with this. I could put a plus sign here, but you can go back and forth between the plus and the minus by changing the sign of omega, just as you did here. So let's do it this way. X cosh omega minus t sinh omega. And t prime going to look similar, but without the extra minus sign here. This, the relation between sines, cosines, and coshes and sinh is one of just leaving out an I. You go from sines and cosines to coshes and sinh by leaving out the I. Well, if you track it through carefully, you'll find that this minus sign was really an I squared. It's not going to matter much, I will just tell you. It really came from some I squared. And if you leave out I squared just becomes 1 squared. There's no minus sign. So here's the guess for the formula connecting x prime t prime with x and t. It equals, let's see, x sinh omega minus plus t cosh omega. In this case, there are 2 minus signs. In this case, there was only 1 minus sign. Okay, but let's check. What do we want to check? We want to check that x prime squared minus t prime squared is equal to x squared minus t squared. You're probably asking yourself, what is this omega? What does it have to do with moving reference frames? I'll tell you right now what omega is. It's a stand-in for the velocity between the frames. We're going to find the relationship between omega and the relative velocity of the reference frames in a moment. There has to be a parameter in the Lorentz. These are the Lorentz transformations connecting 2 frames of reference. In the Lorentz transformations, there's a parameter. It's the velocity, the relative velocity. That parameter has been replaced by omega. It's a kind of angle relating the 2 frames, a hyperbolic angle, but we'll come back to that. For the moment, let's prove that with this transformation law here, that x prime squared minus t prime squared is equal to 0. Is equal to x squared minus t squared. I'm getting to that point in the evening where I'm going to make mistakes. All right, this is easy. You just work it out. All you have to use is that cosine squared minus sine squared is 1. You can work that out by yourself, but we can just see little pieces of it here. X prime squared will have x squared cosh squared omega. T prime squared will have x squared sinh squared omega. If I take the difference between them, I'll get a term with an x squared times cosh squared minus sinh squared. But cosh squared minus sinh squared is 1. All right? So we'll find a term with an x squared. When we take the square of the difference between the squares of this and this. And likewise, we'll also find the t squared. The cross term, when you square x prime, you'll have xt cosh sinh. When you square t prime, you'll have xt cosh sinh. When you subtract them, it'll cancel. And it's easy to check. It's a basically one-liner to show that with this transformation here, x prime squared minus t prime squared is x squared minus t squared, which is exactly what we're looking for. Let me remind you why we were looking for it. If we find a transformation for which the left-hand side and the right-hand side are equal, then if x squared equals t squared, in other words, if the right-hand side is 0, the left-hand side will also be 0. But x equals t, that's the same as something moving with the speed of light. In the x frame of reference, if this being 0 is equivalent to the left-hand side being 0, it says that in both frames of reference, the light rays move with the same velocity. Okay. So that's the basic tool that we're using here. X prime squared minus t prime squared is equal to x squared minus t squared. All right, that does follow by a couple of lines using cosh squared minus sin squared equals 1. But what I want to do, let's take another couple of minutes. No, let's take a break for 5 minutes and then come back and connect these variables, omega, with the velocity of the moving frame of reference. Somebody asked me a question about the ether and what it was that people were thinking. Somehow Einstein never got trapped into this mode of thinking. What were they thinking about when they were thinking about the ether? What exactly was the Michelson-Morley experiment? Well, I'll just spend a minute or two mentioning it. Certainly, Maxwell understood that his equations were not consistent with Newtonian relativity. He understood that. But his image of what was going on is that the propagation of light was very similar to the propagation of sound in a material, or water waves propagating on water. And of course, it is true that if you move relative to the atmosphere or move relative to the substance that sound is propagating in, you'll see sound move with different velocities depending on your motion. If you're at rest in a gas of material, there's a natural sense in which there's a particular rest frame. The rest frame is the frame in which, on the average, the molecules have 0 velocity. If you're in that reference frame, then first of all, light has the same velocity that way as that way, number one. And it has a velocity that's determined by the properties of the fluid that the sound is moving in. Okay. Maxwell more or less thought that light was the same kind of thing, that there was a material, and the material had a rest frame. And that particular rest frame was the frame in which light would move with the same velocity to the left as to the right. And he thought that he was working out the mechanics or the behavior of this particular material, and that we were pretty much at rest relative to this material, and that's why we saw light moving the same way to the left or the right. One would have to say then that Maxwell did not believe that his equations were a universal set of laws of physics, but that they would change when you moved from frame to frame. Just happened by some luck, we happen to be more or less at rest relative to the ether, to this strange material. Of course, you could do an experiment with sound. If you're moving through the sound, you can check that the velocity in different directions is different. You do, let's not worry exactly how you do that. That's what the Michelson-Morley experiment was. Michelson and Morley, I suppose, said, look, the Earth is going around in an orbit. Maybe at one season of the year we just happen to be at rest relative to the ether by accident, and some other season, 6 months later, we're going to be moving in the opposite direction, and we won't be at rest. Only at one point in the orbit could we be at rest relative to the ether, so at any other point in the orbit we wouldn't be. So if we measure in November that light moves the same in all possible directions, then in, what's the opposite of November? May. then in May we should find that light is moving with with different velocities in different directions. And he tried it, and a very fancy and sophisticated way of measuring the relative velocity in different directions, but he found that there was no discrepancy, that the light traveled the same velocity in every direction at every time of year. There were all sorts of ways to try to rescue the ether, but none of them worked. None of them worked, and the result was one had to somehow get into the heart of space and time and velocity and distance and all those things in a much deeper way, in a way that didn't involve the idea of a material at rest in some frame of reference that propagated the light. Okay, where are we? I've forgotten where we were when we stopped. Somebody remind me. Who?
What's omega?
Ah, omega. Yeah, what is omega? Forgot, I don't remember what omega is. Ah, how omega is related, not to the speed of light, but to the velocity of the moving reference frame. Here we have two reference frames, xt and x prime and t prime. What's the relationship between them? Well, the whole goal here was to understand the relationship between frames of reference moving with relative velocity between them. Omega is not exactly the relative velocity, but it is closely related to it. Okay, let's see if we can work out the relationship. We know enough to do it. Let's see if we can work out the relationship between omega and the velocity of the moving frame. All right. Again, let's go back to this picture. Here's a frame of reference moving. Let's redraw it. Here's my origin moving along. Okay. What does it mean to say that from your perspective, my frame of reference or my origin is moving with velocity v? Well, by definition, this is not a law now, this is a definition. It says that this line here has the equation x equals vt. That's the definition of this v here. My origin moves relative to your origin. It moves with a uniform constant velocity. That's an assumption that we're talking about two inertial frames of reference. And you, in your frame of reference, will write x equals vt. That's the definition of v, if you like. What will I call it? I will call it x prime equals 0. All along there, I will say x prime is equal to 0. It's my origin of coordinates. Okay, now let's come to this transformation law here and see if we can spot how to identify v. Well, x prime equals 0, that's this trajectory moving at an angle with a velocity v. X prime equals 0 is the same as saying x cosh omega equals t sinh omega. X prime equals 0, set this side equal to 0, and that says that x cosh omega equals t sinh omega. All right? So whatever the connection between velocity and omega is, it must be such that when x prime is equal to 0, x cosh omega equals t sinh omega. Well, let's look at that equation. It also says that x is equal to sinh omega over cosh omega times t. Well, that's interesting because it's also supposed to be equivalent to x equals vt. Now I know exactly how to identify what the velocity is as a function of omega. The velocity of the moving transformation, the moving coordinate system, must just be sinh omega over cos omega. That's the only way these two equations can be the same. X equals vt, x equals sinh omega over cos omega times t. So now we know it. We know what the relationship between velocity and omega is. Write it down. The velocity of the moving frame. Now this is not the velocity of light, it's just the velocity of the moving frame must just be sinh omega over cos omega. Well, actually, I want to invert this relationship. I want to find sinh and cos omega in terms of the velocity. I want to rewrite these Lorentz transformations. Where are they? I want to rewrite these Lorentz transformations in terms of the velocity. That's the familiar form in which you learn about it in elementary relativity books. X prime is equal to something with velocities in it. To exhibit that, all we have to do is to find sinh and cos omega in terms of the velocity. That's not very hard. Let's work it out. The first step is to square it. And to write v squared is equal to sinh omega squared over cos omega squared. That was easy. Next, I'm going to get rid of sinh omega squared and substitute, where is it? I lost it. 1 is equal to cos omega squared minus sinh omega squared. All right, so wherever I see sinh omega squared, I can substitute from here, namely cos squared omega minus 1 is equal to sinh squared omega. So here we are. This is just equal to cos of omega squared minus 1 divided by cos of omega squared. Or let's multiply by, what I want to do is solve for cos omega in terms of velocity. I want to get rid of all these cos's and sinh's of omega and rewrite it in terms of velocity. So first multiply by cos omega squared. We have cos squared omega times v squared equals cos squared omega minus 1. Or it looks to me like this is cos squared omega times 1 minus v squared equals 1. What I've done is transpose, cos squared times v squared minus cos squared itself. That gives you cos squared 1 minus v squared equals 1. Change the sign. Can everybody see that the second line follows from the first? I'll give you a second.
Put the 1 on the left-hand side and then put the v squared. Put the 1 on the left-hand side and then put the v squared on the right-hand side.
Yeah, it's clear. Okay. Finally, we get that cos omega is equal to 1 divided by 1 minus v squared, but now I have to take the square root. Cos omega divide by 1 minus v squared and then take the square root. And that gives you cos omega. Now, we've all seen these square roots of 1 minus v squared in relativity formulas. Here's where it begins to come. Here we begin to see it materializing. What about sinh omega? Let's also write down sinh omega. Well, from here, we see that sinh omega is just equal to v times cos omega. This is easy. Sinh omega equals v times cos omega. So, sinh omega is v divided by square root of 1 minus v squared. Let's go back to these Lorentz transformations over here and write them getting rid of the trigonometric functions, the hyperbolic trigonometric functions, and substituting good old familiar velocities. Let's get rid of this and substitute the good old ordinary velocities. Okay, so we have here x prime equals x times cosh omega, and that's divided by square root of 1 minus v squared. Then there's minus t times sinh omega, which is v over the square root of 1 minus v squared. Or if I put the two of them together and combine them over the same denominator, it's just x minus vt divided by square root of 1 minus v squared. I think most of you have probably seen that before, maybe slightly different. Let's clean it up a little bit. X prime equals x minus vt divided by the square root of 1 minus v squared. What about t prime? T prime is equal to t minus vx over square root of 1 minus v squared. T prime is equal to t times cosh. Cosh is just 1 over square root. And then x times sinh, that gives us the extra v. In other words, the formulas are more or less symmetrical. And those are our good old Lorentz transformations. Now what's missing is the speed of light. Let's put back the speed of light. To put back the speed of light is an exercise in dimensional analysis. There's only one possible way the speed of light can fit into these equations. They have to be modified so that they're dimensionally correct. First of all, 1 is dimensionless. Has no dimensions, it's just 1. Velocity is not dimensionless unless, of course, we use dimensionless notation for it. But if velocity is measured in meters per second, then it's not dimensionless. How do we make v squared dimensionless? We divide it by the square of the speed of light. In other words, this v squared, which is here, which has been defined in units in which the speed of light is 1, has to be replaced by v squared over c squared. Likewise over here, v squared over c squared. Now, velocity times time does have, notice first of all, the left-hand side has units of length. The right-hand side, this is dimensionless. X has units of length, but so does velocity times time. So this is okay. This is dimensionally consistent as it is. But over here it's not. The left-hand side has dimensions of time. That's all right. 1 minus v squared over c squared, that's dimensionless. This has units of time. But what about velocity times x? Velocity times x does not have units of time. In order to give it units of time, you have to divide it by c squared. Okay, let's check that. Velocity is length over time times length divided by c squared. That's length squared. Oh, it's correct. It's correct. All right, this is probably familiar to most of you who've seen relativity once or twice before. These are the equations relating two different moving coordinate systems moving relative to the x-axis. But you see, the deep mathematics, or the mathematical structure of it, in many ways is best reflected by this kind of hyperbolic geometry here. And you know, most physicists by now never write down the Lorentz transformations in this form, much more likely to write them in this form. Easier to manipulate, easier to use trigonometry or hyperbolic trigonometry. It's a little exercise. It's a nice little exercise to use the hyperbolic trigonometry to compute the compounding of two Lorentz transformations. If frame 2 is moving relative to frame 1 with velocity v, and frame 3 is moving relative to 2 with velocity v prime, how is 3 moving relative to 1? The answer is very simple in terms of hyperbolic angles. You add the hyperbolic angles, not the velocities, but the hyperbolic angles. The hyperbolic angle of 3 moving relative to 1 is the hyperbolic angle of 3 moving relative to 2 plus 2 moving relative to 1. And then you use a bit of trigonometry or hyperbolic trigonometry to figure out how you do the cinches and coshes of the sum of two hyperbolic angles. Very straightforward. And I'll leave it as an exercise to see if you can work that out. Much easier than anything else. Okay, so there we have the Lorentz transformations.
That's very analogous to the rotation.
Yeah. Oh, absolutely. Yes. That's a good point. Yeah. That's right. If we have frame 1, let's call this x1 and y1, x2 and y2, and finally x3 and y3, well, then the angle of 2, let's call it, of 3 relative to 1, let's call it theta 1, 3, is just equal to theta 1, 2 plus theta 2, 3. The angle connecting frame 1 with frame 3 is just the sum of the angle theta 1, 2 plus theta 2, 3. So in that respect, the Lorentz transformations are much simpler in terms of the omegas. It's the omegas which combine together to add when you add velocities. Now, how different is omega from the velocity? Let's work in units in which the speed of light is equal to 1. Where is our formula for velocity? All right, let's take this formula over here. What is sinh omega for small omega? Let's put the c squared there. Let's not put the c squared there. I'll not put the c squared there. Sinh omega is essentially omega when omega is small, just like sine is omega is theta when theta is small. The sinh function, the cosh function looks like this. The sinh function looks like this. But it crosses the axis with a slope of 1. For small omega, sinh omega is proportional to omega. For small velocity, 1 minus v squared is very close to 1. If the velocity is 100th of the speed of light, then this to within 1/10,000th is just 1. If we're talking about velocities 1/1,000,000th of the speed of light, then this is very close to 1. And so sinh omega and velocity are very close to each other. Let's see what's going on here. Thanks. Okay, so for small velocities, omega and velocity are the same. The actual correct statement is that v over c is like omega. The dimensionless velocity over the speed of light is like omega for small omega and small velocity. So for small velocity, adding velocities and adding omegas are the same things. But when the velocities get large, the right way to combine them to find relationships between different frames is by adding omega and not adding velocities.
When you add omega, like compounding velocities as you've got up there, I guess you won't go greater than 45 degrees, I guess, because that would be faster than light.
No, but omega, no, you see, the speed of light is v equals 1.
Yeah.
That corresponds to omega equals infinity. Yeah.
Okay, so you can,
Yeah, so omega runs over the whole range from minus infinity to infinity, but when it does, v goes from minus the speed of light to the speed of light.
so you can add any omegas and it's still.
Add any omegas. Omega, that's right. There's no speed limit on omega.
It's just like when you draw on that diagram, it looks like it's greater than 45 degrees up there.
Where?
With the omega. I guess
Omega is the
that's
distance
theta.
along the hyperbola.
Yeah, that's right.
Sorry, where are we?
Right there.
to the
I
right.
guess that's theta, though, isn't it?
This is theta. That's theta.
Okay.
Yeah.
All
Yeah.
right.
Right.
All right.
Right. Right.
Yeah,
Yeah.
omega is the distance along the hyperbola.
That's right. Distance. That's right. Omega is a kind of distance along the hyperbola. All right. Now let's talk about that a little bit. All right. Now that we've established the basic mathematical structure of the transformations, I think we should go back and talk about some simple relativity phenomena and derive them. Oh, one thing which is important, which well, let's see, here are my Lorentz transformations over here. I said we ought to, at the end, make sure that our transformations are not too dissimilar from Newton's. In particular, when the velocities are small, they should reduce to Newton. That's all we really know. Or at least that's all that Newton really had a right to assume, that when the velocities are smaller than something or other, that his equations should be good approximations.
Isn't adding velocities good enough? Isn't velocities adding good enough?
In fact, you're right. In fact, you're right, but let's just look at the transformations themselves. All right. As long as the velocity is a small percentage of the speed of light, and ordinary velocities are what? 100 miles an hour versus 186,000 miles an hour? What is that? It's small, right? And it's doubly small when you square it. So for typical ordinary velocities, even the velocities of the Earth around the sun and so forth, fairly large velocities, what, 60 kilometers per second or something like that. 60 kilometers per second is pretty fast. That's the orbital Earth around the sun. It's pretty fast, but it's nowhere near 300,000 kilometers per, no.
Yeah.
No, it's 300,000 meters per second. Wait, sorry. 3 times 10 to the 8th, no, 300,000 kilometers per second. Right. 60 kilometers per second, 300,000 kilometers per second, small fraction, and then square it. So for ordinary motions, this is so close to 1 that the deviation from 1 is negligible. So let's start with the top equation. For the top equation, this is negligible, and it's just x prime equals x minus vt. The bottom equation here, you have a c squared in the denominator. Whenever you have a c squared in the denominator, that's a very, very large thing in the denominator. This is negligible compared to t. So here the speed of light is also in the denominator. Just forget this, and it's just t, but it's just t prime equals t. It's just t prime equals t. So in fact, Newton's formulas are essentially correct for slow velocities. No significant departure from Newton until the velocities get up to be some appreciable fraction of the speed of light. Okay, let's talk about proper time. Proper time, and then let's do a couple of relativity examples. Yeah, question?
In that bottom equation, t prime, when x is very large, wouldn't you get a difference of
Yes.
if it was small?
That's right. When x is exceedingly large, you get a correction. But that correction, that x has to be very large. Look, let's discuss before we do anything else. Let's talk about that a little bit. X minus vt, 1 minus v squared over c squared. Yeah, let's. All right, in my drawings, I'm going to set c equal to 1. But in the equations, you can leave the c there. Okay, this equation we understand. Apart from this 1 minus v squared over c squared in the denominator, it's just this x equals vt, or x minus vt. That's Newton. Let's look at this one over here. Okay. Let's look at the surface t prime equals 0. T prime equals 0 is the set of points that I, in my moving reference frame, call time equals 0. It's what I call the set of points which are all simultaneous with the origin. Right? T prime equals 0 is just every place in space-time which has exactly the same time according to my frame of reference, and I will therefore call all those points synchronous at the same time. What do you say about them? If t prime is equal to 0, that says that t is equal to v over c squared x. Now let's set c equal to 1 for the purpose of drawing. Just for the purpose of drawing, I don't want this huge number c squared to distort my drawings too much. It says that t equals vx. What does the surface t equals vx look like? It looks like this. T equals vx, which is also x is equal to 1 over vt. So it's just a uniform line like that. All of these points are at different times from your reckoning. This one's later, this one's later, this one's later, and so forth. According to my reckoning, all these points are at the same time. So we disagree about what's simultaneous. This was the hang-up, incidentally. This was the basic hang-up that took so long to overcome, that took Einstein to overcome it, the idea that simultaneity was the same in every reference frame. Nobody, in fact, it was so obvious that nobody even thought to ask the question, is simultaneous, does it mean the same thing in every reference frame? No, it doesn't. In your reference frame, the horizontal points are all simultaneous with respect to each other. In my reference frame, what I call horizontal, what I call simultaneous, you do not. Okay, so simultaneity had to go. Let me point out one more thing about these equations. I'm not going to solve them for you, but I will tell you the solution anyway. How do you solve for x and t in terms of x prime and t prime? Well, think about it in the case of angles. Supposing I have a relationship like x prime is equal to x cosine theta, what is it, plus y sine theta, and y prime is equal to x minus x sine theta plus y cosine theta. And supposing I want to solve for x and y in terms of x prime and y prime, you know what the solution is? Just change theta to minus theta and write that x is equal to x prime cosine of minus theta. But what's cosine of minus theta? Right, cosine theta, plus y sine of minus theta, what's sine of minus theta? Minus sine theta times y. And likewise for y prime. Y prime is equal to minus x times sine of minus theta, so that becomes plus x sine theta plus y cosine of minus theta, which is cosine theta. You don't have to go through the business of solving the equations. You know that if one set of axes is related to the other by rotation by angle theta, the second one is related to the first one, or vice versa. The first one is related to the second one by the negative of the angle. If to go from one frame to another, you rotate by angle theta, then to go from the second frame back to the first, you rotate by angle minus theta. So you just write down exactly the same equations, interchange prime and unprimed, and substitute for theta minus theta. Same thing for the Lorentz transformations. Exactly the same thing. If you want to solve these for x and t, write down the same equations, replace primed by unprimed, and change the sign of omegas to minus the signs of omegas. Change the sign SIGN of all the sinches. Okay? In other words, just send omega to minus omega. And that will solve the equations in the other direction. Yeah?
You just change the v to minus v.
Yes, it's also the same as changing v to minus v. Yes, the way to see that is to go, right. What was it? What did we have? Cosh omega.
Well, v equals sine h over cosine.
Yep. Yep, that's right. V is sine. Yes, that was correct. Yeah. When you change omega to minus omega, it has the action of changing v to minus v. You can just check that from the equations. Good. All right, let's talk about proper time a little bit. Proper time. If you're doing ordinary geometry, you can measure the length along a curve, for example. And the way you do it is you take a tape measure and you sort of tick off equal intervals, equal little separations. You can think of these separations as differential distances, ds squared, small little differential distances. And that differential distance is dx squared plus dy squared, where the x squared and dy squared are just the differential increments in x and y, dx and dy. This is ds. All right, so that's the way, and you add them up. You add them up, that's the way you compute distances along curves. It's quite obvious that if you take 2 points, the distance between those 2 points depends on what curve. Not the same for every curve. So measured along a curve, you have to know not only the 2 points, but you have to know the curve in order to say what the distance between those points are. Of course, the distance between along a straight line, that's well defined, but the distance along a curve depends on the curve. In any case, ds squared equals dx squared plus dy squared is the basic defining notion of distance between 2 neighboring points. If you know the distance between any 2 neighboring points in a geometry, you basically know that geometry almost essentially completely. So given this formula for the distance between 2 points, you can compute, if you like, the distance along a curve. Of course, you've got to take the square root of this and then add them up. Don't add the squares, add the differential distances. All right. The important thing is here that square root of dx squared plus dy squared, which is the distance between neighboring points, doesn't depend on your choice of axes. I could choose xy axes. I could choose x prime, y prime axes. If I take a little differential displacement, dx and dy, or I just take 2 points, 2 neighboring points, don't even give them labels, and measure the distance between them, The distance between them should not depend on conventions such as which axes I use. And so when I make rotational transformations, the x squared plus dy squared doesn't change. The x and dy may change, but the x squared plus dy squared does not change. The same thing is true in relativity, or the analogous thing. We don't measure distances along the paths of particles. Let's say now that this curve here is the path of a particle moving through space-time. There's a particle moving through space-time. And we want some notion of the distance along it. Right? The notion of distance along it, another example would just be a particle standing still. There's a particle standing still. Particle standing still is still in some sense moving in time. I wouldn't want to say that the distance between these 2 points in space-time is 0. They're not the same point. I wouldn't like to say it's 0. I would like to say there's some kind of notion of distance between them. But it's quite clear that that distance is not measured with a tape measure. This point and this point are the same point of space, boom here at this point of space, and that at a later time, boom again at the same point of space. 2 events at the same point of space. How do I characterize in some nice way the distance between those 2 events that occurred in the same place? You don't do it with a tape measure. All right? What do you do it with? A clock. A clock. You take a clock and you start it at this point. Tick, 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 tick. And a stopwatch. You press it at this point, tick, 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 tick. It ticks off intervals. And then you stop it at that point and you see how much time has evolved. That's a notion of distance along a particle trajectory. It's not the distance the particle moves in space. It's a kind of distance that it's moved through space-time, and it's not 0 even if the particle is moving, standing perfectly still. In fact, what it is it's the time along the trajectory. What about a moving particle? Well, you can imagine that a moving particle carries a clock with it. Of course, not all particles carry clocks, but we can imagine they carry clocks with them as they move. And we can start the clock over here and end the clock over here. What is the time read off by this moving clock? The time read off by a moving clock is much like the distance along a curve, measured by a tape measure. In particular, it should not depend on the choice of coordinates. Why not? This is a question that has nothing to do with coordinates. I have a clock made in the standard clock factory. The standard clock factory in, I don't know where, in Switzerland someplace, makes a certain kind of clock. That clock gets carried along with the particle, and we ask how much time evolves, or how much time elapses, or how much the clock changes between here and here. That should not depend on a choice of coordinates. It shouldn't depend on a choice of coordinates because it's a physical question that only involves looking at the hands of the clock. In fact, we could ask it for little intervals along the trajectory. We could ask how much time elapses, according to the clock, between here and here. Well, the answer, again, should not depend on what coordinates you use, which Lorentz frame you use. And there's only one invariant quantity that you can make out of the dx's and dt's describing this point, describing these 2 points. There's a little interval dt, and there's a little interval dx. Now we're in space and time, not ordinary space. And the quantity which is invariant, there's really only one invariant quantity that you can make out of it. It is dt squared minus dx squared. It's the same quantity, x squared minus t squared, for a whole, for a whole interval dt squared minus dx squared. That's the quantity which is invariant. It's minus it's the negative of what I wrote over here, x squared minus t squared. Okay. This quantity is equal to dx prime squared minus dt prime squared minus dx prime squared. The same algebra goes into this as goes into showing that x prime squared minus t prime squared equals x squared minus t squared. Incidentally, this is the same as saying t prime squared minus x prime squared equals t squared minus x squared. Doesn't matter which way you write it. All right, so that suggests that the time read off, the invariant time read off along a trajectory between 2 points separated by dx and dt is just the square root of dt squared minus dx squared. Why the square root, incidentally?
Well, you're going to integrate it d tau.
Well, I can integrate dt, yeah. Well, all right, why not just dt squared minus dx squared for the time between here and here? Here's an answer. Supposing we go two intervals exactly the same as the first one. We go an interval over here, dx and dt, and then we go another dx and dt. What happens when we double the interval to dt squared minus dx squared? It gets multiplied by 4 because everything is squared. Well, I wouldn't expect a clock when it goes along, when it goes along a trajectory for twice the interval here to measure 4 times the time. I expect it to measure twice the time. So for that reason, the square root is the appropriate thing here. Okay, that's called d tau squared. D tau squared, the proper time along the trajectory of an object.
Well, that's just d tau.
You're right, that's just d tau. Or d tau squared being dx squared minus dt squared. D tau is called the proper time. Let's go. I think let's see. The tau is called the proper time, and it is the time read by a clock moving along a trajectory. It's not just dt. That's the important thing. It's not just dt. dt squared minus dx squared. Let's do one last thing. Let's just do the twin paradox in this language. I think I've had it. I'm going to finish. You can do the twin paradox in this language. All you have to do is to compute the proper time along 2 trajectories. One that goes out with a uniform velocity, turns around and comes back with the same uniform velocity, versus a trajectory which just goes from one point to another point along a straight line. And it's no more weird, it's no weirder really from this perspective than saying the distance from one point to another along 2 different curves do not have to agree. The proper time along 2 different curves in general will not agree. What is a little bit weird is that because of this minus sign, the proper time this way is less than the proper time this way. That's the consequence of this minus sign here. Moving with some dx decreases the proper time. All right, we'll do a little bit more next time, but then I want to get to the principles of field theory and connect some of this with field equations for interesting wave fields.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.